Thanks, everybody, for being here. My name is Jesse Russell. I'm with GDOT. I work for Justin here. So I have the distinct and totally not stressful pleasure of introducing my boss, my boss's boss, and my boss's boss's boss. So here we go. Starting with Justin. Oh, and Dee. Let's not forget Dee. All right. So starting with Justin. Justin's graduated Georgia Tech with over 10 years in the industry with GDOT. He spent time in D5 and D6, D5 and D7, traffic operations offices, as well as the state traffic operations office. His current role, he serves as assistant state signal engineer, traffic engineer, sorry, that's me, leading the state signal operations and maintenance programs, as well as advancing the state's connected vehicles goals, which we're going to talk about today. Justin is a proud husband and father, and probably most importantly, has just coached his son Henry's 3-year-old Braves T-ball team to an undefeated season. So, yeah. Yes. That's a competitive league, so. All right, so Alan is next. So he has over 15 years of experience, Alan Davis, with traffic and transportation sector in both South Carolina and Georgia. He's worked in the public sector for the majority of his career, serving in roles ranging from traffic signal engineer to his current role as the state traffic engineer for the Georgia Department of Transportation. In this role, Alan oversees the department's traffic signal and arterial management systems, freeway and incident management, ongoing safety improvements, traffic studies, deployment of intelligent transportation systems, and the deployment of the connected vehicle vision. Alan is a graduate of University of South Carolina and enjoys in his spare time spending time with his wife and his 2 sons, Finley and Cal. John Hibbard is with GDOT. He's the Operations Division Director for the DOT. His responsibilities include the oversight and direction of the State Maintenance Office, the State Utilities Office, the Office of Traffic Operations, and the Office of Transportation Data. So John does not do much. 36 career. He has a 36-year career in transportation technology, includes stops at several national consultancies as well as local government. He's a graduate of Georgia Tech, imagine that, and has a bachelor's and master's in civil engineering. And Dee, last but not least, now this is a fun one. Dee is currently the SIGOPS East Metro Deputy Project Manager of GDOT's AECOM contract since the Metro's inception in November of last year. He's currently a member of the National Committee of Uniform Traffic Control Devices as Secretary for the Signals section. He's the zone manager for RTOP for almost 8 years now, and prior to this was the City of Gainesville's traffic engineer for 10 years. In the late 90s, he worked for various consultants supporting GDOT's conversions to the 2070 controllers and GDOT's Railroad Crossing Evaluation Program. Prior to that, he worked for Norfolk Southern and Delta Airlines. So he's been around the block. Dee is here shopping for antique traffic, but this is my favorite one. Dee is here shopping for antique traffic signal equipment while being closely supervised by his wife and 2 children.
Thanks, Jesse. We are already short on time, so we'll move fairly quickly here, but I'm excited about this really conversation as we envisioned it today. I'm hoping it to be a little bit for y'all like it has been for me the last 6 months, stepping into trying to help take over the connected vehicle program with a couple of these gentlemen. And really, a lot of it has been like this, conversations, asking each other questions back and forth and finding out what's going on in the industry. So as you go through it, if you have questions, we're hoping to field them. I'm not sure we're going to have too much time, but I hope, that we're more than willing to talk about it. And yeah. Quick overview of what we're going to do today. I'm going to try and talk just a little bit about connected intersections for anyone who doesn't quite know specifically what we're pointing to, and then start pulling in these gentlemen with some questions, really to just provide their perspective as they've been through this initiative. It's been going on, I think, Alan was telling me yesterday, 20 years, which was a little longer than I realized. really want to touch why we're pursuing connected intersections. It did not dawn on me the implications really that are out there immediately, not just in the future. And so we'll touch on that and then get into some very specific applications. As we're talking about those applications, I think, there's some specifics that affect, I think, everyone in this room that you can start doing today to really make sure that the V2X initiative takes hold and that we see all the benefits we hope to realize from it. And then finally, we've got a bit of a call to action and hopefully speaking to individual roles within the room on what that means for you. So connected intersections. Overall, what you have is your signal controller. On that signal controller, the way GDOT has it set up is a CV app is collecting SPAT and map data from the controller and then translating or passing that to a roadside unit. You'll point to you. Yeah, there we go. And that is what broadcasts the SPAT and map data out to a vehicle, which can then process it on a CV app in the vehicle. And so really, when you're talking about connected intersections, the definition is fairly simple. It's infrastructure which broadcasts SPAT and map data. SPAT is shortening for signal phasing and timing. Map is generally giving you information about that location, the layout of it, so that cars can understand how to process data related to that intersection. Additionally, we're passing that information via routers and via fiber to our central system, as well as passing that to open data APIs, which can then share that data with third party. And so a lot of that, what we want you to take away is that this is, this has been designed by GDOT and by others in the industry to be open source and provide data to third parties so that they can use it. And that is a deliberate choice that's been made that enables a lot of important applications. Additionally, alongside all of this, ITE has been working with OEMs, infrastructure owner-operators, a lot over the last few years on an initiative to develop a standard for connected intersections so that infrastructure owner-operators understand exactly what we need to do to help enable connected vehicle technology. Within that standard, and it's published online, and we can provide those links, but there is a strong focus on data quality coming from agencies, and that's not just, are we giving you the data, but is the data accurate? Is the data secure? There's a big focus on security, obviously, and that's not just, whether or not there are certifications for an intersection passing information to a vehicle, but really, once this data is out there and can be manipulated, it's important to have your entire system designed front to back with security in mind, and so that's a big focus. One we've also talked a lot about is the need to enhance vehicle to infrastructure communications, and so GDOT, I found out a lot the last several months, is very much a national leader in how much communication we have with our intersections. Folks in this room and OEMs, giving OEMs the confidence that if they start pursuing this technology, start investing in it, that it's going to be worthwhile, and that requires a lot of us in this room. So some more pictures in case you can't quite see what's up here, but on the left, you'll see on that pole above the road signs, you'll see an RSU, a roadside unit. It's got antennas. You'll see these at well over 1,000 intersections throughout the state. And that's, again, what is broadcasting out the message to vehicles. In the top and the middle, you see a small blue device. That's an onboard unit that sits in a vehicle. We've also got an example of an application that was developed in-house with GDOT and SWERI, and Alan might want to touch that can run on it. And then we can see Max Time CV, which is an application that runs on our controllers to broadcast that or to pass that information to the roadside unit. So hopefully that visualizes it, gives you a little bit of an understanding if you hadn't seen any of this before. Now, what we really want to get into is why are we touching on all this stuff? Why are we putting all these devices at our signals? Why do we need them in all of our vehicles? First and foremost, and we'll get into a very specific example, safety benefits. There is a specific intent to eliminate crashes with this that can be tackled soon. Operational benefits that we'll touch on as far as traffic signal optimization. Transit signal and emergency services, providing preempt and priority to those vehicles. That's already being done throughout the state. I think what this technology can do that is different is by deploying it at all of our intersections, we make those initiatives things that we can tackle immediately. Some Something big is redundancy and reliability. We'll touch a little bit on this, but I know a lot of folks here are probably thinking, can't an autonomous vehicle do some of this stuff? And we have been having, well, maybe not me specifically, but some of these folks been having conversations with OEMs, and they've told us specifically that they need more information from us that will make their systems more redundant and reliable, and that those implications are real. We have data that no one else has, on our signal controllers that we need to pass to them. So that's really big. So this is interesting, and it really, to me, it shows how real CVDX is, or VDX is, excuse me. There was a map at the beginning that showed over the 1,000 intersections we're pursuing, but really the last month or so that I was prepping this presentation, every day there seemed to be something pop up that was critical for vehicle to infrastructure. And this was one that popped up last week. The commissioner was speaking in a presentation, and he wasn't talking on this, but it came up. And this is a crash that happened in early January of 2020. It was about 3 in the morning on the Pennsylvania Turnpike. And what happened was a bus was coming down. It was slightly raining, down an incline and around a curve, and lost control on the Pennsylvania Turnpike. And it actually came to rest basically across traffic lanes on its side, and then was struck by, my notes, but multiple trucks. I think it was UPS and FedEx trucks, as well as a passenger vehicle, and 5 lives were lost, about 60 injuries in total. And it's really interesting. The NTSB reviewed that and concluded, one, that existing autonomous vehicle technology likely could not have prevented that crash, and furthermore recommended pursuit of V2X technology as a potential countermeasure. And while this isn't an intersection, I think it's a big statement that to that redundancy, that reliability, yes, there's vehicles already trying to prevent these types of crashes, but with infrastructure, technology, and passing more information to those vehicles, we can prevent crashes and we can save lives. And that's what we mean when we say reliability and redundancy, not just more data. Did anyone want to touch on that?
The NTSB has gotten very interested in the connected vehicle discussion recently, and the session that our commissioner spoke at, one of the other speakers was a board member of the NTSB, Michael Graham, and he's got some passion on this topic. And so the fact that they came out as they completed their investigation of this crash, and they investigate all crashes, and that was a commercial vehicle and lives were lost, they investigate. That they came out in that and said that connected vehicle technologies would have made a difference is a big deal, and goes to their increased focus in this whole topic that we're talking about now.
And again, titles connected intersections. This is not an intersection. I'll just be clear on that. But I think, building out more radios, more communications, providing more information, showing that it's feasible is really critical to making things like this work one day. And again, building that trust with OEMs by going through that, and connected intersections is something that we can very quickly tackle today to prove out that VI vision. And so more touching on reliability and redundancy, Andrew Heath, who had a conversation recently with Hyundai, he was telling me about, and one, you can see some of the information up here on the screen. Maybe it's legible, but they're looking for Q data, speed limits, speed zones, reduced speed zones like school zones, road and pavement temperature, ambient temperature. And this is information that they can pass to their ADAS systems, advanced driver assistance systems, which, again, yes, they're trying to do this in their vehicles alone, but they've told us they want that data. Something that I think is really cool that we heard or Andrew heard from them was they are considering removing sensors on vehicles as part of that. And that's not just a cost savings. I think it shows that we have the potential, by building out more technology on the public side, to make the entry point for potential life-saving applications cheaper, which, it speaks to it's critical, I think, to lower that cost of entry point. These shouldn't just be available to the Lexus and the Audi, but hopefully on your entry-level vehicles. just want to dive into some applications. Hopefully you're sold a little bit on the critical need of this, but there's several applications. All of these are demonstrated ones, and this is, I'll say, a Frankenstein of presentations Alan's done over the years. And so these have really been going on for multiple years, but red light warning is a big one we're going to touch on specifically. Phase service time remaining we'll touch on, and green speed for coordinated signals. There's also emergency vehicle pilot freight that was just being highlighted in the e-commerce session. So diving into red light violation warning. This application, what it does is it takes SPAT and map data from the signal, and then a vehicle can process that along with its speed and position data to determine whether or not it is going to approach a green light, if it needs to slow down and stop for that signal. And really what it's aiming to do is tell drivers if they're about to unintentionally enter a signal on red. Certainly you're gonna have some drivers who blow on through that, but a lot of your distracted drivers or a driver who's newer to an area, you know, if that notification pops up and says you're about to possibly enter an intersection on red, that's gonna reduce a crash potentially, and that's at least 700 fatalities, 90,000 injuries per year that you're trying to capture with that. And so it's a very real application that's been tested and proven. What I want to let Alan get into is this is not as simple as you might think, and it's really got some goals that we need to tackle now.
Yeah, and the red light violation warning idea, application, whatever you want to call it, is really what the Connected Intersections ITE project spoke towards. It was on top of the existing standards that we have now, what additional clarity in data, refining of data, additional bits of information need to be passed from infrastructure to a vehicle to make this, on the auto side, ready to deploy a safety application happen. And it's happening in 5 milliseconds time of information passing. It's fueling automated driving systems. It's alerting drivers to this situation of an imminent crash or imminent risk associated at an intersection where you're crossing. And so working through that to really build on this work of, like Justin said, of 20 years of, we spent probably 100 or 200 folks in the industry over really throughout the course of the pandemic to work through this, to fight through this on various aspects of this application, all the way from components of the signal controller. What bits of data is coming out of there? What does it mean? Imagine trying to explain how a traffic signal works to men and women that build cars. We speak different languages. When you talk to them and say, when they say, what do you mean signals aren't fixed time? Well, there's this thing called actuation. Why do you do that? Stop doing that. No, we're not going to stop doing that. We've been trying to get that working for 40 years now. That's an interesting conversation, and it took a lot of back and forth to really communicate how we approached running an intersection and then what their needs were to enable a life-saving application. And one of these slides, the slide Justin has up here, go to the one before this one, Justin. Yeah. The one after this, sorry. There you go. One of the big takeaways from this was, traditionally a traffic signal makes a decision about its next phase pretty close to when it turns. It's about 100 milliseconds for some of the manufacturers that's going in there. When it actually has all these inputs and says, all right, I'm going to go to the side street now. It makes that decision quickly. And so what that results in is this moment where if you were looking at a visualization of the signal data and one of those countdown applications like we had, like Justin showed on some of the screens there, is it would jump from, the timer will go to 0 and then turn. And the automaker said, no, I need, I need some time where I have absolute confidence of when this light is going to change. Okay, well, how much? I don't know, 2, 3 seconds, something like that. So essentially they need a period of 2 to 3 to 4 seconds, depending on the speed and geometry of an intersection, of absolute confidence that a traffic signal is going to change its phase. So that gives them time to either make, on the vehicle side, a decision to stop or go when they're approaching a red light. And that's really important for red light violation warning, that have that accurate amount of data. But to enable that, there's a lot of things you have to change in how the controller operates. There's a lot of things you have to consider as a signal operations engineer like Dee, of do I want to sacrifice efficiency on my side streets or my minor movements to enable a safety application? That's a tremendous trade-off we have to make on the infrastructure side to say, I can scrap this bit of efficiency for 700 fatalities every year, Justin, 90,000 injury crashes. That seems like a reasonable trade-off. But just to show the next slide there, Justin, if you will, what that looks like. And this is, again, enabling red light violation warning. And we went out and kind of noodled around with a few settings in a signal, and the controller timing settings to kind of trick the controller to doing this application, this assured green period, as it's called, where there's that 100% confidence of what the signal is going to do. So you'll see, this is going to get in the weeds, guys. You'll see the signal count down and hang out around 9 seconds. So you see the all red time, the yellow time, and this assured period that we trick the controller into providing. And so it hangs out there at what, 9 seconds? Is that right? And then that's in a period where the chord window, this is a coordinated traffic signal, could serve the side street. But we had assured an amount of time that it wouldn't immediately transition if a call came on that side street. So no call in this video you're watching here, no call came on that side street, so it went back into its chord window, and then you for that phase, jump back up to 60 seconds. So here we have a controller now providing this information over an RSU into an OBU to be able to make this decision of, okay, I have this window of time where I could run a red light violation. This was done in a very non-standard way. If you actually look at the data being spit out by the RSU, it was garbage and not usable, but it made it work for the application. And it just goes to show the effort that still needed to be made on the intersection level to figure this stuff out, to refine those standards, to have it approached in a common way. And it may be as simple as we'll just make our phase change decision a few seconds earlier, or it may be something where there's a more dynamic equation and algorithm running in the background to enable that.
And so, like Alan said, this is in the weeds. We understand that, and then we're not intending folks to come out of here knowing how to provide assured green time at their intersections. But I think something critical to take away is that a lot of folks do affect the things that we'll be setting up in controllers in the future. A lot of folks can have an effect on those applications, and they will no longer be as simple as a yellow maybe running longer than it should have, but will be a potential life-saving application if you keep that dialed in. And so it's important as you progress to make sure folks understand the critical need of these settings, that it's important when you're approaching a signal for this information that you get that map information, that location-based information from the intersection, so that it can help you understand in the vehicle which lane you're in and whether or not a certain left turn, yellow or red, is applicable to your vehicle. And so that map information is something that in the future we're going to have to be very aware of and handle in a very delicate way. And something as simple as downloading the wrong map location information to the wrong location because you had to replace the controller could affect whether or not these life-saving applications work. And so those are all things, maybe you're not working with these applications today, but you do work with controllers today, and those are things we need to make sure throughout our organizations and throughout our agencies and companies that we're addressing.
Justin, that's a really good point, is that if you're using these devices on the side of the road and speaking to vehicles directly or indirectly, you're essentially enabling a digital traffic control device. It's a digital traffic signal. If you go up and put up the wrong head on a span or a mast arm and tells the driver the wrong thing, turn right instead of left, that's a problem. You wouldn't want to do that digitally to a robot car. You essentially have a new driver here you have to consider. So that's the assurance to quality here is very important.
Let's try a new application. Maybe even more in the weeds, but I think pretty cool. And the guy in the video you'll find also thinks it's really, really cool. And I forgot to introduce CAMP, but it's a group of OEMs and researchers working together under an LLC to research these things, build out proven applications at intersections. And so this is another one of their applications called Tosco, traffic signal, or not traffic signal, just traffic optimization for signalized corridors. But it takes more of that SPAT and map data in. It also, what it needs from a signal controller, a traffic signal, is queue information, and not just, you know, your setback loop and your presence loop, but it really needs queue information all the way throughout that signal. But once you have that data, a vehicle can make decisions on its own as it's approaching a signal, say, that's about to turn green, but there's a queue built up. Do I need to slow down and coast a little bit into this intersection to avoid stopping altogether? Do I just need to go ahead and stop? It can also enable things like a coordinated launch. And so I think the video speaks a lot. It's a minute long. But what you're going to see is vehicles approaching an intersection and then doing their thing. So you
The
can see that
fundamental scenario for Tosco is a string of vehicles will come to a stop at an intersection. The light is red, the vehicles will come to a stop, all 4 vehicles will come to a stop in unison, and then they'll wait. When the light turns green, they will launch in unison. So you'll see all 4 vehicles. It's really a tremendous sight to see. All 4 vehicles moving forward at the same time, maintaining that space, that predetermined space, right? We've got to set it about 3 meters. And the vehicles will maintain that space as they go through the intersection. And then once they reach a certain speed, then they'll start to spread out in order to maintain one, in this case, we're a 0.6 second headway. So as the vehicles move faster, then you'll see the space open up. But time-wise, it'll be constant for 0.6 seconds.
abrupt ending coming here, but
We wanted to see what would happen if we upped the speed limit. See what happened.
you know, I think to certain signal folks in the room where you maybe lean a little bit closer to the guy speaking on the video, that is just tremendous to see all those cars launch off from a signal altogether. And maybe not as cool to other folks in the room, and I can understand that. But you can see also just in the top right, there's kind of a diagram there. There's multiple scenarios that are enabled with an application like this. I think it also has safety implications to help you identify a queue and hopefully prevent a rear end crash, which is very common from an installation of a new signal. But Alan might be ready to jump in.
Sure. But I'm going to throw it to Dee.
Yeah.
You know, John and I actually got to go ride on this demo in live traffic, and it was pretty impressive. 4 cars from 4 different automakers independently driving this corridor in an automated mode, but also kind of ad hoc working with each other in that uniform launch and stopping. But it was enlightening that they needed very accurate queue information from infrastructure. So not just is there a vehicle present at the stop bar, but how many, how far back? Dee, how good's our detection?
Work in progress, Your Honor. Yeah, I think it speaks to the accuracies of the data that it's collecting is how good is our infrastructure. And, you know, we're blessed in this state with a lot of avenues to improve that infrastructure. And it's really on everyone in the room that either is a part, one way or the other, of the SIGOPS program to recognize deficiencies and line up avenues and bug that guy who then bugs these guys to get the funding in place so that we can get good data out to these users. I mean, it kind of goes back to, you think back, I don't know, 8 years, how many of these were out on the street? Kind of like the electric vehicle presentation yesterday. You guys talking about, 20 years ago, there was 1 or 2 makers, and now all of the automakers, and they're all moving towards electric vehicles. Well, these are built right in. The onboard units are built right in the newer vehicles. So there's going to be a lot more users, is my point. So we have a responsibility for maintaining all of our devices, not just these devices, but the communications, the detection, and increasing the reliability of the information.
And I mean, that's, you know, you've heard me say, hopefully, that we're trying to build trust and relationships with OEMs, that their investments are going to be worthwhile, and that's what we're trying to speak to. And if we don't provide that reliable resource to them, these applications just don't work. There's no trust there. There's no desire from them to continue those efforts.
Yeah, and they've made it abundantly clear to us, infrastructure owner operators, they don't really care if we spit the data out and it's got the security certificate on. They still don't trust us. It needs to be reliable. It needs to be accurate. It needs to have that level of precision, as well as all the security layers and all that stuff. Because they're going to deploy these systems in their cars to which they hold a liability for. They're not going to rely on our data if we just kind of wing it and say, it's within 15 seconds. That's good enough. The clock's good enough. It's not drifting that much. This level of precision that's going to be demanded of us by this industry and by public when they have this stuff in their vehicles is going to be a lot. And we'll have to, we as IOOs and our partners who help us deliver this stuff will have to really step up to meet that challenge.
So something else, and I think it's relevant to probably several of the folks in this room, you know, I can understand connected intersections, this conversation. It can feel very urban. It was something we discussed as we prepped for this, and really wanted to stress upon the group that we don't feel it's just an urban only perspective. There are implications to the rural world, and John wants to talk about that.
We worked with the Ray, and I don't think Laura is here today, but she was yesterday part of that EV session. And we worked with them and Panasonic and Kia, because the Ray is right there where the Kia plant is in West Point, and did a more than proof of concept, but it was showing the use of connected vehicle data in an open road, in a more rural interstate setting, very successful. And we were able to install the onboard units inside Kia vehicles that are essentially assigned to and used by that plant in long-term test applications. We were able to show potential weather implications up ahead. A vehicle that might be passing through rain could pass that information to cars behind or nearby it. The presence of a work zone, which that's a critical thing. It's a big thing that all of the automakers want, as well as all of the data companies that want to guide us to our destinations. They want to know work zone information. Connected vehicle technology could be, or it can be, and was demonstrated as a very effective, near instantaneous way to pass that information to cars. That was all done on this segment of I-85. It's out there. We've got roadside units scattered along that segment of the roadway, because the intent is that these things, although we have focused our work here in Georgia on these in conjunction with traffic signals, SPAT and MAP messages, that's a traffic signal based sort of app. The intent is that this device stands to be present everywhere, not just at signals, but along the road to provide information that is relevant to the vehicles passing by, to potentially provide certain unique special things. If you can envision some sort of odd geometry, might be a good reason to put in an RSU in a more rural setting. And so that was something that we just finished with them. And all parties regarded as very successful. Understand that Kia plant there in Georgia, Hyundai coming in Bryan County, it's all the same company. They're all part of the Hyundai empire. So what's going to happen here in Georgia stands only to grow and be more significant nationally in this whole vehicle automation connectivity sense.
You know, there's a couple applications that Dee's working on with some folks in regard to transit signal priority and emergency vehicle preempt, but I would stress again that, while those applications, they've been done before without V2X technology, at least the way we're envisioning it, by deploying this at all intersections, we enable those things to happen much more quickly, openly. And yeah, Dee, do you want to speak to any of those applications?
Yeah, there's no one here from Gwinnett, but the Gwinnett Smart Corridor is kicking off in a couple of weeks. It's basically a soup to nuts kind of deal where they're rolling out the devices themselves, approximately 175 intersections, having the app loaded on the 1C CPU, and then we're assisting. Is Chala? I don't know if Chala's in the room or not, but yeah, Chala is doing a lot of the timing implementation for the TSP, for the transit signal priority. Gwinnett also has a couple of locations, and they're also utilizing the same infrastructure to support their emergency vehicle preemption at several currently at several fire stations as pilot programs, and then rolling that out. And then of course we have the project on West, I don't know, down on West Peachtree that was done 18 months, 2 years ago. So that was transit signal priority. So the stuff is not only coming, but it's here, and yeah.
So, please.
If I could, though, on that, back up real quick. As you look at that laundry list of things down the left side, you'll see some of them, you'll say, oh, that's old news. We've been doing transit signal priority. That's not a new thing. No, it isn't. But all of those things, both the ones that are familiar to you and then the ones where you kind of scratch your head and say, I don't know about that. They all happen using the same technology. We don't need a gadget to do transit signal priority and then another gadget to do SPAT and MAP and then another gadget for freight signal priority and on and on and on. No, it's all this. Just load it onto this. So you can see an efficiency there and a standardization in terms of how that information is passed. So you can get a sense of a broader impact on it, non-proprietary impact. But a key to it, and you might want to advance the slide at this point, is if we're going to participate in all this high-tech vision of the future type stuff, we got to do the basics. We got to be doing the basics and well. So when Dee talks about detection, yeah, got to have it. Communication, all of this stuff, the concept, relabeling what we've always called interconnect or communications, maybe we call it backhaul, because that's what the telecom industry calls it. And that's increasingly the comm network that ties all of this stuff together is increasingly critical. And frankly, it's a thing that vaulted GDOT into such a national leader in this business because we already had so much fiber interconnect, connecting all of those signals, all of those SIGOPS, formerly RTOP signals. So we already had a big chunk of the whole connected vehicle puzzle in hand.
And so the intent here was really to try and address everyone in the room, especially anyone who feels that this might not be related to them. I can easily see how you could approach this and say, that's not me, that's the SIGOPS guys. They're going to figure it out. Thanks. But, there's multiple ways to approach this problem. From a design perspective, there's a really critical need to approach the way you design an intersection right. We're running short on time. But, choosing intersection detection that is not just designed as intended and according to the manual, but that is reliable and that will help address future needs is critical in that regard. And so we think ITS and signal designers do need to understand the fine details of vehicle detection to enable some of this to work as best as possible. I'm glossing over it, I apologize. IT information technology and security is essential to making this stuff launch. I don't know if you have high points on that, Alan, but.
Yeah, I'll since you're rushing us through, Justin. each one of these messages coming out of these things has if they're following standards, will have a security layer that says, "Hi, I'm Alan. I'm coming from a trusted source. You can trust me." And then there's that handshake that happens that verifies the message between an application and the source. But that's just one piece of security. And part of the connected intersections discussion we had with automakers and security experts in the industry, it's like, no, we need to have an understanding of your entire network. What are you doing to keep bad actors out? How are you securing your physical infrastructure in the field, at your data centers? What are your audits, your systems, your automated alerts? It's a systematic approach to IT and security that, regardless of however many high-tech things you stick on your intersections or on your freeways, it's something as an agency you should be approaching anyways. And so it's that bigger picture of security that needs to be considered at large.
And so our final pitch here, this is the GDOT V2X roadmap. It was created before I arrived over, and we're already working on the next iteration of that because it is a quickly moving piece. But I think one big highlight is we have secured funding about $7-8 million a year for the next 10 years to build this out. And so you'll see us go from well over 1,000 intersections to all 6,500 in those 10 years. 6,500 intersections with basically this V2X technology enabled, roadside to units deployed. And as part of that, a strong plan to work with our fleets, GDOT's fleets like Heroes, as well as emergency vehicles, transit vehicles, to start enabling some of these applications that we've been talking about today. Not sure if anyone has any more high points they want to hit.
I'll jump in with one more thing, or two more things really. Dee mentioned the work that was going on in the Gwinnett County Smart Quarter. That's actually a GDOT held contract. It is an open agency contract, and so it is available for use across the state. Reach out to Justin if you want to look into that. Gwinnett County did a lot of interesting things there through the Georgia Tech Smart Communities Initiative to have something that's scalable beyond just Gwinnett County. But since it's a state-owned contract, there's a lot of flexibility and usage there. And I'll add too that the over 1,000 RSUs that have been deployed have been done through a lot of hard work for a lot of our partners. So real quick, if you've worked on the SIGOPS program, raise a hand. You may not know it, but you've had a part in deployment of this. The Atkins Sweary team, who deployed hundreds and hundreds of these things all across the region, our local partners who are now funding in pieces of this through the Atlanta Regional Commission and GDOT. Everybody's been a big part of this, whether you realize it or not, and it's making Georgia a leader in this space, and it's going to lead to us having more safe and more efficient operations on our roadways. So also, I'll let you get that, Justin. Also, Q-Free Intolite for a lot of the back-end infrastructure that's allowed us to be successful in this space as well.
And we really wanted to have some questions. We've got another panel that's got some really cool applications that ties in well to this. So I don't know if we're going to have time for them. I'm going to be respectful of their time. They've got less than, I think, 50 minutes or 40 minutes to go. So we'll transition here real quick. One question.
No. The only vehicle that has ever been deployed in the U.S. that I know of with a functional onboard unit were Cadillacs back in 2015, 16. And there were probably, I don't know, 20 to 50,000 of those made. There were numerous automakers who had plans to outfit their entire fleets, notably Toyota in 2018, Ford, that they were going to hit 2022, all having to roll back their plans due to regulatory uncertainty in the space.
Here's what I've heard. I'm been very fortunate to attend comfortably more than my share of conferences, and I was at the SAE WCX, which would be roughly their equivalent of TRB, just as geeky as TRB. And what became clear throughout that, whether it was from university researchers, the R&D people at automakers, or the more straight-up production automakers, as well as other pieces of the U.S. federal government, is the idea that vehicles need to be connected to each other and to the infrastructure is a given. It's not a question of should we, maybe, how. The how is not clear, but the should we, maybe, it's like, no, it's gotta be. That the safety benefits are abundantly clear and everybody gets it. So frankly, I'm very annoyed at where we sit right now because I wish I could give you a much stronger answer. But what I find some comfort in is the overall pan industry, and the industry is the automaking industry and much less our industry. That connectivity's gotta be, just gotta happen.
That's it for these guys.
Okay.
Well, it's the best. Yeah. All right, I'll start with Jared here. Jared Wall is a senior engineer with Kimley-Horn, and he's EPM for Kimley-Horn SIGOP Southwest project and 3 Jared was a traffic signal engineer for the city of Austin, Texas, before he moved here to Georgia, and is a graduate of Georgia Tech in 2012 and the University of Texas at Austin 2013. I didn't know that about you. Kyle Huffman is a senior traffic and ITS engineer with AECOM. Kyle attended Georgia Tech, which he received his BS in civil engineering in 2009 and his master's in civil engineering in 2010. He's been working for 12 years in the industry. He specialized in traffic signal timing operations and has designed and implemented new traffic signal timings over 1,000 traffic signals throughout the Southeast. He's a registered PE, and he and his wife Ashley live in Smyrna with their 1-year-old son. And Mike DiSanza. Mike is with AECOM. He grew up in Boulder City, Nevada, a little town outside of Las Vegas known as the home of Hoover Dam. Much of his youth was spent running through the deserts of southern Nevada, catching lizards and snakes, camping, fishing, participating in recreational math programs, and playing music. When he was 19, he decided to move up to Portland, Oregon with his band to make it big. After 2 years of kind of trying, they called it quits, and Mike struck out for the East Coast, landing in Savannah. In Savannah, he started a successful career as an electrician and a traffic signal tech, and has played in more bands than you can count on one hand, where he met his wife, Amanda. In 2013, Mike and Amanda welcomed their daughter, Artemis, into the world, and now they live, well, they were in Chattanooga. Now they live in Rising Fawn, Georgia, where they live like gurus at the top of a mountain. He is currently AECOM SIGOPS North project project manager for D1 and D6. Deputy. Yeah, I don't want to say. Don't elevate me too high. Right. So today we're gonna give you a lot of examples. And sorry, we're basically gonna just run through and nerd out with you for about 45 minutes. So anyone who's not prepped for that, leave now. Custom programming meets safety and operations. So to the Q Free, is Q Free in the room right now? There he is. Well, this is going to be a very basically an advertisement for you. So we work with your software, your signal software throughout the state of Georgia. Anyone who doesn't know, MaxTime is our statewide signal software, and we slide. So essentially, our sorry, in Max Time, we have two systems. We have User Logic, and we have our peer-to-peer, and we kind of, Alan and his group touched on that with the connected vehicles. Peer-to-peer is essentially Max Time's way of communicating between signals. So one controller can connect to another. User Logic is basically a system within MaxView, which allows us to custom program certain, operations for specific locations, usually trouble spots. So we're going to run through a few applications, basically pattern overrides, railroads, some peer-to-peer stuff, and then we touched on a little CV, so we'll probably leave that off the list at the end. But
Yeah, thank you, Jesse. This is just showing, we kind of wanted to give a representation of just where we're touching in Georgia. We, between the three of us up here and Jesse, we cover, just about 5 of the 6 SIGOPS regional contracts, and these are the examples we're going to go over today. And then, there we go. So we're going to try to be aware of the time. I know that we're up against lunch, so if we do have to go a little bit long, that's going to be okay. But so Jesse talked about the first application being a pattern override. So with user logic, essentially what we're doing is we take some kind of external stimulus and we're going to apply at our local controller some type of response. This one here was in Atlanta, right at the I-20 eastbound on-ramp. There's the ramp meter that's run by the ITS group. And they approached us a couple of years ago back in the RTOP days, and we're trying to come up with a way that we can keep the ramp meter on longer. So that there was a big issue. This is just south of the downtown core in Atlanta. And there's a big issue where, right at the PM rush hour, everybody comes out of downtown Atlanta. They try to take that left turn onto the on-ramp, and it just ends up overwhelming the ramp meter. The longer the ramp meter is on, the better the operations is for the freeway. So we wanted to try to meter traffic into the ramp meter. And so this was a perfect example of how we can use user logic. So what we do is, can I click with this? Okay, yeah. All right, so ramp meter turns on. You see the light turn all 3 colors. And so what we immediately do is, using the peer-to-peer communication between the ramp meter's controller and our controller, we've received that signal that the ramp meter's turned on at this intersection that controls the intersection of Capitol Avenue and the on-ramp there. We kick into an alternate pattern. And that alternate pattern, what we're doing is we're just limiting the protected split for the southbound left turn. So we're trying to meter the flow of traffic onto the ramp and use a lot of the capacity that we have on that bridge coming down from the State Capitol building to store some of those vehicles. And by doing that, we can keep the operation of the on-ramp or the ramp meter a bit longer. So we'll zoom in a little bit longer or a little bit closer here. This is some drone footage that we took of it in action. So we're in that pattern 32. We got the southbound left turn splits a little bit shorter, and as that queue starts to back up, then there's a second step that we implemented to try to improve operations a bit more. That last vehicle comes in there and it hits that queue ramp at the top of the on-ramp. Now what that's going to do is it's going to trigger the flush for the ramp meter. But before that happened, what we want to do is shift again to even a smaller cycle length, just to start cycling traffic through a bit quicker now that we know that we can't process any more vehicles onto the on-ramp. Here's another example. This is down in District 4. This is SR 520, major east-west corridor in the state. It's a very critical corridor throughout that area. And it hits this huge bottleneck right at I-75 where we've got this intersection at Virginia Avenue. It's wide median, split phase north-south. We've got the 2 on-ramps there with I-75, and the way they're configured is any westbound traffic on or off the interstate has to take a left turn. Chick-fil-A restaurant, which I don't need to go into any more detail there. And the issue that we were experiencing was that we would just get these sporadic backups of westbound traffic going through the area, and it was really quick when it would come on. We didn't think it was necessarily the right application for traffic responsive because we wanted something that would react really quickly to it. And it was just this little 5-signal area. So what we did was we set up, and I'm going to zoom in just on these 2 signals at the ramp. We have the setback detector loops on those 2 intersections, and we developed a system where if we've experienced a 90-second period, and this is through a lot of trial and error, so don't ask me how we got to these numbers, it's just months and months of trial and error. But what we ended up with is if there's a 90-second period with no gaps greater than 5 seconds across all 4 of those detectors, then we've identified that that westbound queue is now overwhelming the cycle length that we have in place. So across all 5 of those intersections, we're going to kick it into a higher capacity cycle to just try to move that westbound traffic a bit further along. I said higher, yeah. And what the release is going to be, so once that we've experienced a 30-second gap in traffic across both intersections, then at that point, we say, okay, we're back to normal, and we'll go back down to that regular cycle length. And this is just showing that we have, we can tie it to whatever pattern that we're running in the time of day plan. If our AM pattern has a certain balance, directional balance of traffic, then that pattern 12 is going to be the higher capacity one. It's going to have that same balance, but it's just a bigger cycle and have more capacity.
All right, had another example of pattern override. Something happens. So normally, your corridor, southbound relationship these 2 signals, and the heavy right turn, the right turn's really not that heavy typically. They can just build a block and get started green. However, when there's an incident, everyone starts bailing out. Characteristics change and prioritize the off ramp. So luckily here I had some ramp detectors. Basically what I did was, if those ramp detectors reach a certain occupancy, then I'm changing the splits and offsets to prioritize traffic. It all happens automatically in the background.
All right. In this example, what we've got on the screen, if you can see where the corridor is there's a few signals that we're actually running traffic responsive. In that case with traffic responsive, the central system is calling a pattern. It's not guaranteed to be running at any certain time of day. So when you throw a school into the middle of a traffic responsive system that has dedicated bell times and dedicated traffic patterns to that school, we wanted to make sure that the school signal, the signal there at the school, was always being served what it needed to be. We've used a couple of different things to do that. In some cases, we've used queue responsive on a local controller, but in this case, our team that was working on the old RTOP 2 project, this one was done by Scott Yonker and Wilberg, came up with this, which is a pretty neat solution that also kind of worked in conjunction with the crossing guard staff that were out there. In that bottom right-hand picture, you can see what kind of looks like a push button. There's actually a little key in there, or lock type thing, and the crossing guard has the key to it. When the crossing guard turns the key, it actually calls a special function in the controller. And then through user logic, once that special function is active, the controller then compares what the actual pattern that's running in the controller, so whatever TR has picked, the controller will identify that, and then that program is mapped to a corresponding pattern in that local controller that will help flush the school traffic in. So through user logic, we've developed basically pattern mapping so that controller will adjust its patterns, effectively becoming almost an adaptive type split based on when that key is turned. There was an additional program in there that actually set up some queue responsive stuff as well. But that was a very kind of neat and unique way to call these things, I think. And the idea with that pattern overrides in general is to be able to adapt to traffic, to be able to do the things that traffic needs out there kind of on the fly. So we like this one a lot. All right, I get to hold the mic. So the next thing we're going to talk about is the peer-to-peer stuff. Like we said in the introduction, Peer-to-peer is basically, controllers talking to each other. Why do controllers need to talk to each other? It's to share information. And so we've come up with a number of different ways to share information between the controllers and a number of different reasons to do that. The first one we're going to talk about here, we call this Pseudocord. What we had here is two intersections that are about 1,100 feet apart. And the traffic patterns out there didn't really lean towards, like a fixed time of day schedule that we run coordination on. We were really concerned about side street delay if we added a, coordinated programming out there, just because of the way the arrivals are. And so what we came up with was peering these two detectors together to share, or these two controllers together to share their detector inputs. And then it basically became coordinated through detection. So maybe on-demand coordination is a good way to put it. And since it's demand-based, there's really no increase in side street delay out there at all, or perceived side street delay anyway, because the people on the side street aren't just sitting there waiting through unutilized green time that you'll get sometimes in coordinated systems. So the way that this one works is the, say westbound detection at Mac Smith is passed over to the signal at Lakeview Drive, and through we got kind of complicated with this one, so I'm not gonna talk too deeply into it, but through the user logic we've basically developed, and kind of like Jared said, how did we get to the numbers? It was through a bunch of trial and error, a period of detection extensions and delays to get the timing that we wanted and the relationship that we wanted between those two intersections. So basically working at kind of like an offset. And the entire goal was to, kind of reduce stopping between the intersections. If you leave one, we're gonna try to get you there on green. We may or may not do it, but if you look at the AOG charts that we've showed for before and after, we were able to improve the AOGs by 16% by adding this program to it. And again, it's all demand based, so we were pretty happy with the way that it turned out.
This really the exact same thing Mike just talked about. Stole this from him. But it was a great application for pedestrian hybrid. Eventually, I'm peering the adjacent detection hybrid. What that allows me to do is just make sure that I don't truncate that platoon of vehicles that actually. So it still runs free. One platoon comes.
And yeah, another very similar example to Mike's. Calculus was invented twice. We were kind of doing similar things. This was an example where we actually did have coordinated systems, but these are two one-way pairs in Douglas, Georgia, where the north and southbound direction sets lined up so that we could coordinate traffic across both. But what was often happening if there wasn't enough, I'll use the example of, the intersection on the left there. If there wasn't enough demand on the stop bar detectors at that left intersection, then a car coming westbound across from the right intersection may not get there in time. So we simply just peered those detectors, the stop bar detector on the right side across to the east intersection, or to the west intersection. And what that does is it calls up, instead of the standard minimum green time of 5 seconds, it calls up a longer one of 15 to 20 seconds. I don't remember the exact number. And then once so that gives that car more time to get across to the other intersection. And then as that loop is actuated while the phase is green, it extends it longer than our program passage time. So it extends it 8 seconds just to give it more time to get across. So since we've done that, we're not having to put any kind of recalls on the side streets, but we're still able to get that coordination that we wanted across both. Another example similar to Kyle's PHP. This is one we were approached by City of Peachtree City, where they have this PHP for mostly golf carts, but also pedestrians, that was in really close proximity to this major intersection on SR 74, which wasn't part of a coordinated system. And the spacing here is such that, you know, if that was a traditional signal, it would definitely be an ideal candidate for coordination. But the volumes at 74 and Crosstown intersection were such that we wanted to leave that in free. We didn't want to try to coordinate it. But the issue they were having was during the PM peak, the southbound left turns at SR 74 were very heavy. Oftentimes that eastbound through movement was very heavy. And if that golf cart pedestrian crossing was actuated at the exact right time, that traffic could back up into the main intersection. And so there's a little period, about an hour there in the afternoon, where that was becoming an issue. So rather than peering detector status, we peered phase status. And so the way that this works is, here's our phasing diagram for the SR 74 and Crosstown intersection. And the only thing that really matters is that phase 4 eastbound and the phase 5, the southbound left turn. If phase 4 is on, or has been on, if phase 4 has been on for 20 seconds, then any actuations at the PHP are going to just be delayed. What we're going to do is we're going to hold the PHP, not serve the crossing until either phase 4 is ended, and then that would continue on until we have, when phase 5 has been identified as the next phase, if phase 5 is green, or about a 7-second extension after phase 5, just to clear a bit more through. And then once both of those conditions are no longer met, then we'll allow that crossing to serve. Then we've also tied it to a time of day function, so it's only active from 5 to 6 o'clock in the afternoon. The city wanted to put this sign up just to give a bit more communication to the users that this is something that could be expected, because otherwise it runs free operation, and like the PHPs, we get that used to that instant service. So we wanted to kind of give them a message that they may not see that. Another application here, we flew the drone over to the Atlanta streetcar. We'll see the animation here, but this is where the streetcar over on the east end, it comes up Edgewood Avenue, takes a left turn to go up Jackson, and then a left turn on Auburn to go back into the downtown core. And the issue that we had here is we had a detection device for the transit vehicle at the Edgewood and Jackson intersection, but we didn't have one at Auburn. So rather than installing a detection device at Auburn, what we did was we just, using peer-to-peer and user logic, can kind of get the same operation with just the one device at Edgewood. So the way that we did it was, streetcar shows up. I'll see the streetcar there. That's what it looks like from above. And then I showed that little gold star there. That gold star is an Opticom device. It's identified that the streetcar is in the area. And what that does immediately, this is without user logic or anything, it puts in a call for will be the eastbound left turn phase at Edgewood that serves the transit vehicle. And then this next stage right here, the Opticom device is still on. The eastbound left turn, the transit phase is on. And so the combination of those two conditions being met is what puts in the call for the transit phase up at the Auburn intersection, so that we lined up the offset so that we know that whenever it gets up there on the next cycle, that call has already been placed. It's going to be locked in. And we didn't need to have an additional device at that other intersection. And there's that being shown.
All right, we'll jump into some railroad stuff here. Y'all probably are familiar with Millen. Even if you're not, I saw some of the Augusta guys here. Y'all came through Millen on the way here. It's a very highly trafficked truck corridor and train, being between Augusta and Savannah. So really, I'll go through basically what the issues were here and how we're using user logic to fix it. So we have 6 main points of egress coming in and out of the city. They're all state routes. And we have 3 mainline crossings that can be blocked here. And the problem with Millen is they can be blocked for hours at a time, up to 8 hours at sometimes. Because in the middle of town, they have the loading bay. So they'll stop trains there to load them. Basically, we have 7 different blockage scenarios, or a combination. So three of the blockages are a combination of the 3. So basically what we tried to do is we came up with 3 different phases and 3 different approaches based on what side of town you were in. If you're approaching from the the southeast, then the main blocking of concern is the one at Recreation Drive. So essentially, this is the simplest of the two. We've basically peered the crossing intersection that we have a preemption call at. We're taking that preempt call to the flasher further up the road. And basically, anytime that there's a crossing there, that flasher will go off and warn truckers, don't turn down that way. And I should have mentioned at the beginning, the reason where we're really trying to fix the problem when it comes to trucks is they don't have the room to turn around that cars do when they get stuck by a train. So really what we're trying to do is just provide that advance warning throughout the city. So we have this flasher here, and then they can easily go around and hit the bypass on the other side. We have the second phase here. Sorry, I think I clicked too many times. The second phase here is another crossing. We have 2 crossings here. I'll just go ahead and show you a picture. Here's a train that was stuck there for a few hours, but we have a camera that's watching the flashers at the crossing. It's kind of a Utilicom's here somewhere. I think I saw Mark Falbert. He's been helping me out with this. We essentially just watch for the flashers, and every time there's a flasher comes off, it puts a phase 2 call into the controller. We have a controller at that camera. It's peer-to-peer to the intersection close by, which we have a phase 2 recall that comes in. That turns on blank out signs located at each approach, so that when when trucks are pulling in, they see that sign go off, and they know, the train is too far down for them to see. So they just know that there's a train there, find another route. And phase 3, sorry, I'm jumping through this. Phase 3 is still ongoing, but we're actually using a PTZ camera to catch the train itself, not the flasher. So we're gonna detect the train, and this is actually the same camera system that's being used on wrong-way detection for the express lanes in and out of Atlanta, which is really cool technology. So, but we have 3 different DMS signs that we're going to put up around. Those are already installed. We're waiting on some timber poles to be put up for the camera right now. But as soon as we get that active, we basically will have 8 different message signs that can pop up based on what crossings are blocked. So we'll be able to really just divert trucks around town based on these message signs. And hopefully I'll be back next year to let you know how it went.
Yeah, I can kind of gloss over this one. This one kind of combines a lot of the things we've already talked about: pattern overrides, railroads blocking roadways for long periods of time, peer-to-peer. What this is in downtown Griffin, it's the intersection of SR 155 and SR 16, pretty major route in Spalding County. And there's a railroad crossing you see kind of up at the top of the screen of those faint green lines, right next to a switch yard where not exactly sure why, but trains will come across the tracks and they'll stay for up to hours at times, blocking SR 155. And there's not really a good at-grade crossing nearby for anybody to divert to. So what we did was just something simple where if we picked up a 4-minute presence on the railroad preemption at that nearest intersection, we take that group of signals in the downtown system and we kind of shift that prioritization where SR 155 is our main route, and we shift it over to this local street, which is 6th Street, just adjacent. There's a bridge that goes across the railroad there. And as soon as that railroad crossing is blocked, we just kind of make that the main line in terms of the balance of traffic flow that we have through an external pattern command. Here's another application where we wanted to modify the operation of the blank out signs for this particular set of locations. Because the way that the turn prohibition blank out signs work in traffic controllers normally is they're just tied to the preempt status. So the preempt comes on, the blank out sign comes on. The blank out sign doesn't go off until that preemption turns off. So there's 4 distinct preemption intervals that occur. And this is what would typically happen is there's that entry interval where the train is approaching, the traffic signal controller has picked up on the call that the train's coming, and there's whatever phase happens to be running. We're trying to end that phase so that we can serve the track clear phase. In this case, the track clear phase is going to be the northbound and northbound through. What we noticed at this location was that if that parallel route to the railroad track was green, at this point during entry, there's a couple seconds where a lot of cases will have it where as soon as the rail comes in, that entry phase is almost doesn't last any time at all, and it just goes immediately to track clear. But in some cases, if there's a pedestrian crossing that we don't want to just entirely truncate the flashing don't walk interval, we'll shorten it a little bit, and that's what we did here. So there could be 5 or 6 seconds where this entry phase stays on. We didn't want to immediately pop up that blink out sign and prohibit the turn. The gates are still up at this point. We could give conflicting messages to drivers, and we saw that at this location, that was kind of an issue. So what we did was we just rewrote the logic for how those blank out signs operate, where the sign does not turn on at this stage. Instead, once we get to the track clear is when the blank out sign would turn on. So we're at track cleared now. We're clearing traffic off the tracks. The gates will come down soon. So want to get as many cars off the tracks as we can. And then we go into the dwell interval. During the dwell interval, this is when the track the crossing is blocked, and we just will go to serve the phases that are not conflicting with the rail crossing that can still be served. We'll have the blink out sign on there. And this is the other thing that we changed. So with the traditional operation, it'll go into an exit phase. The exit phase will typically be the same as the track clear phase, where that northbound direction will be green. We didn't see any reason to continue to keep the blink out sign on during the exit phase. So like this, the right turn for that eastbound traffic, the gates have gone up. There's no reason to really hold them back. So we just modified the operation so that instead of running during all 4 of those intervals, it only runs during the blink out sign only runs during that interval 2 and 3, the track clear as well. Another application, this is just one where we had a crossing that would get blocked, and it'd be a series of several signals that would get backed up, and what we were seeing was that on exit, we weren't clearing out all the demand there. So what we did is we created this Preempt 2 that automatically kicks in as soon as a rail crossing drops. So that first preemption goes away, and then this Preempt 2 kicks in immediately. And all that does is it just holds those phases green until that existing queue that's built up during the rail crossing is cleared out.
All right, I got another example of railroad application. Here we got a railroad that runs parallel to Covington Highway and crosses Turner Hill Road. And it's really closely spaced to the I-20 interchange also. So the challenge here is if a train comes through at the wrong point of the cycle, at the wrong time of the day, there's potential to be a standing queue in the way of the track clear. So GDOT already has a long-term solution for this. The project underway to improve the bridge, add advanced preemption, but we want to do what we could right away with user logic. So essentially what we're doing is if Covington Highway goes into preempt, we also preempt the interchange ramps, flush out all the southbound traffic. It was uniquely easy to do in max time. This is just one line of program introducing another preempt. And then a short max presence so that the freeway ramps immediately start going back into chord. The track clear is done.
Oh, next one.
Then at the same location, it's not uncommon to have long trains, slow trains, or stop trains. I see preempts over 30 minutes there quite a bit. So as you can imagine, that causes some pretty big backups on Turner Hill Road. So after a few times of manually calling up the PM plan to flush it out, I was trying to figure out a way to automate it. So essentially what I'm doing is if the preempt lasts 10 minutes or longer, once the preempt clears, I'm calling up the PM plan for those 5 signals, which the PM plan is essentially a southbound flush. And then finally, at the same location, this kind of goes back into a pattern override. While watching it, we started seeing an alternate route that everyone was taking along preempts. So essentially, I'm just saying if a preempt lasts 5 minutes or longer, then I want to cut the intersection of State Route 12 at Lithonia Industrial Boulevard free. We got our free settings set up in a way to help flush out that alternate route. And then those free settings are extended for 5 minutes once the preempt clears to make sure everyone gets through the system. And then it worked out really well here. It's the first signal of a coordinated system, so I didn't have to break up a system by cutting it free. All of that happens automatically.
All right. Due to time constraints, I'm going to wrap up here. We have a couple more examples, but I told you we were going to nerd out with you, so I hope you're not disappointed. Yeah, if you have any questions on this, please let us know. We can do some really cool stuff nowadays with max time, and you know, I guess what I'm trying to say, we can single out intersections and not do such a cookie cutter approach, which is what really this allows us to do. And it's a really powerful tool. If anyone's interested in, and if you haven't played with it yet, please reach out to one of us. We actually like this stuff. So
Yeah, and with user logic, the options of what you can do is pretty much it. So if you have a challenge and specific issue, start thinking about what you can do with a bunch of if-then statements. A lot of things that you can accomplish
Yeah, and
pretty easily.
a lot of what we wanted to do with this today was just to go through some of these examples and get everyone out here thinking, industry professionals and stakeholders, of what can be done at a traffic signal. And the most beautiful thing about this is you go out into the state, 10,000, how many locations, everything that we need is already there. You got the controllers in there. We have the communications between those of us on the stage and our colleagues at Gresham and Jacobs. The staff that knows what to do is there. The opportunities are pretty endless.
So on my milling project, that's actually one big reason why we did use the camera system for the flasher, to detect the flasher. Yes, ma'am. Yes, ma'am. It's Utilicom. Yes, ma'am. Yep. And Control Tech is the other, they're doing the other one at the other location. Sorry, Jerry, I didn't mean to steal the mic from you, but that's actually a really big reason of why we didn't direct connect to the railroad with the normal preempt like you would. It's just a time constraint.
And in the blank out example, it's just the shunt that is the railroad preemption that goes into the controller. That's what we used.
Love the
Definitely some lessons learned in the past, and this is kind of our first big foray into let's share with everybody and what we're working on.
I'll say, like Jared said, we kind of invented calculus twice again with some of this stuff. At a couple of meetings early on, Jared and I actually got together back in December to discuss what we were doing between ourselves. We share information internally fairly well. Like Kyle said, he stole some stuff from me, so we've passed that along, but there's definitely work to be done on that. I think one challenge of it, as far as, say traditional repository goes, is it's kind of the uniqueness of the way that the max time user logic section works. And that's a really good point that I think we can probably start working on, is to start developing the documentation of how the user logic is built and share our workflows among that. So, yeah, yeah. Yeah, the key has to be turned off. I don't believe that it can be pulled out unless it's in the off position. So.
Thanks, everybody.
Thank you all.